So the next speaker is going to talk on accelerating NVMe-oF target services via SPDK and DPDK. Mr. Ziye Yang is a senior software with Intel, and he is involved in SPDK, Storage Performance Development Kit development work. Before that, he had worked in EMC for 4.5 years and is interested in system virtualization, file systems, and storage-related research and development work. He currently holds 12 issued patents in the US and 4 issued patents in PRC. He holds a master degree in computer science from Fudan University. So may I please request Mr. Yang to come on stage and enlighten us. Thank you so much.
Good afternoon, everyone. First, I would like to ask a question. How many people hear SPDK before? If you hear that, please put a hand. Okay. So I think it will be a good opportunity for me to introduce SPDK here. Actually, my topic name is Accelerating NVMe-oF Fabrics Target with SPDK and DPDK. It is just a part of work inside SPDK library. So we will have the following agenda. First, we will introduce what is SPDK, and the second part will be the accelerated NVMe-oF Fabrics target and the initiator with SPDK, and finally we have a conclusion. So what is SPDK? Actually, SPDK is derived from DPDK project. Previously, SPDK is our internal project in Intel, and the name is DPDK for storage, and the code name is Vakeke Beach. Then after several years development, Intel open source SPDK, and you can find SPDK in their website, spdk.io. Actually, SPDK is designed with a similar idea in DPDK, but it is used in storage area. Especially, SPDK is used to accelerate the NVMe device, SSD acceleration. And the fundamental user space polymorph driver in SPDK is a user space NVMe driver. With that, you can just drive the PCIe SSDs with the user space drivers instead of the kernel drivers, which is a similar ideas with the polymorph NIC driver in DPDK. And this page just lists the benefits provided by SPDK. For example, the first one is that the NVMe-oF Fabrics target development by SPDK is about 10x better than Linux kernel NVMe-oF Fabrics target. I mean, this is the core performance. And the user space of SPDK's NVMe driver is about 8x better than the Linux kernel. And there are other list of things. I will not go through that. And this page is important. It is the architecture of SPDK. It can be divided into 3 parts: the drivers, storage services, and the storage protocols. The drivers is the fundamental of SPDK. Current SPDK provides the user space NVMe drivers and also the user space IoT drivers. It is a user space CBDMA drivers. And you can see that in the storage service layers, we have several user space block layer, which is similar like the block layer in kernel space. For example, we have the user space block device constructed by user space NVMe drivers. Also, we can also encapsulate the Linux AIO drivers. And we also can construct user space drivers based on Ceph RBD. And we also have several new drivers like the VirtIO SCSI, VirtIO block, which can be used as the initiator in container. Then as the previous talker said, we can use this component to connect the SPDK vhost backend. And with such components, we can build the accelerated user space applications. For example, we can build a user space iSCSI target, and also the user space vhost SCSI block target. Even that, we can also construct a vhost NVMe target. And here, in my presentation, I will pay more attention to the user space NVMe-oF target and initiator. And besides that, we will have following plans to integrate DPDK's encryption framework. We will also would like to integrate Cinder or the VPP TCP/IP stack. So the next part is the SPDK environment abstraction. The reason we need this abstraction layer is that we want to make it flexible for the users. Currently, you can see inside the environmental abstraction, we encapsulate the following components in SPDK. For example, the memory management. Actually, the memory allocation is used for the user space I/O device and address translation. And the second is the PCI enumeration and the resource mapping. And the third is the threading mode. And the fourth is the lock-free and the memory poor data structures. And obviously, DPDK is our default environmental instance or example. For example, we encapsulate as the environment DPDK in SPDK. Definitely, you can replace DPDK with other APIs, but you need to comply with the SPDK's API. But I should say that DPDK's memory management and the PCI management and also the thread modeling APIs, I think currently is the best ones which can be collaborated and used in SPDK. So there is a question with this component, how do we combine the different SPDK components? For example, users want to write a high-performance storage application. So they need the following SPDK components. For example, the user space NVMe drivers and the user space block layers, and maybe the threading mode, for example, run to complete. So how can we achieve that? Actually, SPDK provides the application framework to do that. Inside the application components, we have the four different components. The first is the reactor, and the second is the product. Third is the event, and the fourth is the I/O channel. Actually, you can see the details from this diagram. For the reactor, actually, a reactor is a thread. If you use the DPDK as the default environment library, the reactor will use DPDK's thread to create a thread, and it occupies independent core. For example, in this diagram, if we have n cores, then each core will have a reactor. And the event is the ring, which used to pass the messages among different threads. And the Prola is a specific task defined, which can use to execute functions or timer functions. And the I/O channels is a combination with the thread and the device. Actually, each thread will have its unique I/O channel. More details will be presented in the next pages. So in this page, it is the introduction of the Prola. the parallel is a function or a timer function. For example, in this diagram, the I/O device actually is maybe NVMe device. It has the submission queue and the completion queue. Then we can divide the parallel into two parallels. One parallel is used to submit the I/Os, and the second parallel is used to track the I/O completion with the callback. Then we can add the parallels into the reactors, and each reactor will execute its own parallels by sequence in a loop. And the event, as I said, is that is used to exchange the information among the threads. And in SPDK, we avoid use the mutex. Since for the mutex, it means the lock. And if there are many threads try to acquire the same lock, it will be definitely a disaster to degrade the performance. So we provide the event. Actually, the event ring is provides the cross-thread communication. For the users, the usage is very simple. It's just a function pointer with the argument. It means that you just execute the function with the function pointer with the argument. But actually, the implementation is it sounds a little difficult or hard. Actually, each reactor owns an event ring, and when the reactor A wants to send a message to reactor B, it will allocate an event and call this event. It means that it encapsulates the function pointer with argument into an event, and this event will be added to reactor B's event ring. And finally, in reactor B, it will in the reactor B's function. It is a for loop. It will check the elements in the event ring and extract the event, and finally execute this function with the arguments. And the I/O channel actually, as I said, that it abstracts the hardware I/O queues. If you have the I/O device with the multiple threads access, then each thread will have its own I/O channel, and thus it allows the simultaneous access to the same I/O device without any lock. So this page shows an example of the NVMe-oF fabrics target, how to glue these components together. For example, firstly, when the MF target starts, it will the reactor 0 will start to execute parallel in the acceptor. Then when there are network IOs, the acceptor parallel executes the function, and finally there are IO requests arrived, and it will spawn a new parallel. For example, user asynchronous message, and spawns a new connection parallel in reactor 1. Then when there are IOs are issued to the storage device, there will be another storage parallel. And finally, the storage parallel executes the functions, and when the IO completion is generated, it will just execute that, and finally, we will send the IO complete data to the connection parallel. Then connection parallel will write the IO packets to the network. So this is the first part. I introduced what is SPDK, and the second is the accelerated NVMe-oF fabrics target initiator in SPDK. This page just shows the development history of SPDKs and NVMe-oF fabrics target and host. We started in 2016. Actually, when the first NVMe-oF fabrics specification is opened, we are the first one to implement the NVMe-oF fabrics targeting in user space. It is earlier than the Linux kernel version. And we did lots of useful work. For example, currently, SPDK's NVMe-oF fabrics target can support thousands of connections. And also for the NVMe-oF fabrics initiator, we have the zero copy features like the features in DPDK. And the current SPDK's NVMe-oF fabrics work is based on the RDMA transport. And we use the following DPDK components encapsulated in libSPDK environment DPDK.A library. We use the PCI device management, thread scaling, memory management, and also the log management. And we are also plan to implement the user space TCP, implement the TCP transport-based NVMe-oF fabrics target. The first is the kernel version. And the second is that we may use the VPP, DPDK-based user space TCP IP transport. And it means that we will use the DPDK's Ethernet polymodel drivers and also the relevant user space TCP IP stack. And this page shows the performance comparison between SPDK NVMe-oF fabrics target with Linux NVMe-oF fabrics target based on the RDMA transport. You can see that in the same environment configuration, both SPDK and the kernel can achieve the hardware limitation. In this experiment, we will first achieve the network throughput limitation. But we can see that in this experiment, to achieve such performance, SPDK will only use 3 cores, but the kernel will use 30 cores. So definitely SPDK's performance is 10x better. Actually, we compare the performance again. It is based on the 3 components. The first is that we use the user space NVMe drivers. It reduces the per NVMe I/O overhead. Secondly, we use the RDMA QPR polling, so there will be also no interrupt overhead. And finally, we pinned the connections to different CPU cores. It means each CPU core will handle its own NVMe-oF fabrics target connection, so there will be no lock among the connections. And this page just lists the user space NVMe drivers performance gain compared with Linux kernels. You can see there are 5 different areas. For example, SPDK uses a asynchronous polymodel driver. It is lockless. And we use the user space hardware access instead of system cores. The fourth is that we use the huge pages. And the final is that in kernel, it is used a generic block layer. But SPDK is designed for the special flash latencies. So for both submit I/O and the complete I/O, SPDK is much better than kernel. And this page just shows the performance comparison. If we just use 1 core, one CPU core, you can see that SPDK can linearly increase the performance from 1 NVMe SSD to 8. But definitely, the performance will be down if provide more and more NVMe SSDs. But you can see the kernel, even if you increase the number of NVMe SSDs, the performance cannot be increased. And this page shows the latency compressing between the kernel NVMe-oF fabrics target initiator solution with the SPDKs. You can see that in this diagram, we compare the I/O round-trip time, and in the left part, it compares the latency, the real latency, and the right, it compares the 4KB read and write workload, compare the latency. And we use the Intel's Optane NVMe SSD as the backend. We can see from this environment, this experimentation, SPDK reduced the latency by 44% for read workloads, and about 36% for write workloads. And this page just we just make it clear to the users how SPDK improves the performance. So we divide the I/O round-trip time into three different parts. The first is the fabric arrive time. The second is the device execution time in SPDK server target. And the last is the fabric departure time. In this diagram, we use the SPDK's NVMe-oF fabrics target with the kernel's NVMe-oF fabrics initiator. And we see that the total time, round-trip time is 20 microseconds. And the diagram in the right part shows the division. And if we replace the kernel NVMe-oF fabrics initiator with the SPDK's NVMe-oF fabrics NVMe-off initiator, we can see that the fabric arrive time is decreased from about 7 microseconds to 2 microseconds. And we also decrease the fabric departure time from 6 microseconds to 4.85 microseconds. So next is the conclusion. Actually, to summarize, in this presentation, we introduce the basic components in SPDK. And you know that the fundamental in SPDK is the user space NVMe drivers. And another fundamental component is DPDK. Actually, we use DPDK to implement SPDK's environment abstraction APIs. And the second, we introduce the accelerated NVMe-oF fabrics target and the initiators in SPDK library, and illustrate how SPDK improves their performance. So currently, SPDK is proved useful in many scenarios to accelerate the storage applications. For example, in China, currently Alibaba company, they use the SPDK in their distributed file system in the Pangu, and also the EC2 service to use SPDK's vhost target to accelerate the NVMe IOs inside the virtual machines. So SPDK is very useful. So the last one is that I will call for some action. We are welcome everyone to use SPDK in storage area. You can investigate it and also do some experiment by SPDK's example, like what you did in DPDK. And we also welcome everyone to contribute code and participate in SPDK community. Currently, SPDK is also an open source project. Currently, we have some external maintainers like Suhe in Hitachi, and we are also welcome other external maintainers to join SPDK. Thank you. So any questions?
Questions, please.
Hey, thank you for sharing. Can you go back to your slide deck where you were showing performance with, yeah, this one.
Yeah.
I'm not a storage guy, so let me start off by saying like this. For me, a NVMe
Yeah.
non-volatile memory
Yeah. Yeah.
over PCIe
Yeah.
means it has multiple queues or SERDERs
Yeah.
wherein which you can put read IO ops
Yeah.
on top of it.
Yeah.
So in your example in the previous slides and
Yeah.
all, you
Yeah.
showed one core serving one queue, or is it one core serving one device like SSD, NVMe, or PCI M2 slot? Is it one device or one queue?
No, no, no. Actually, the previous for for this page,
Yes.
this is just an example. Actually, you can see in this page there are can be with many I/O devices. Actually, SPDK, as the previous talkers, it can be scaled. You can just use one core to create multiple I/O queues
Okay.
to the devices.
Okay.
And also you can, for example, if you use the multi-cores, you can divide the I/O queue creation and distribution in other CPU cores.
Perfect.
Yeah.
Perfect. Now, then let me ask a question. What is there in the performance figure that you shared? Here you mentioned it is for 4K random read-write operations.
Yeah.
But if I understand, QD stands for queue depth or queue description.
Yeah. This is the QD is stand for queue depth.
Why queue depth 1 in NVMe? Normally, when if you use ADATA or any other performance crystal benchmark and all, for NVMe SSD, they have either 8 or 16 as queue depth.
Yeah.
But here, why queue depth 1? Is it for latency?
Yeah, this is only for latency, just for illustrated latency. You can see the previous, this is to explain the...
To boost it up?
Yeah, yes.
Okay, so if, like you mentioned for Alibaba and all, where they have virtualized entity running with lot of data storage, to reduce the latency, you kept it as queue depth equal to 1.
Yes, yes.
So what is the worst case performance for smaller size packet? Here it is 4K.
Yeah.
What about smaller size ones? Or 4K is the standard size?
4K is the standard size.
For NVMe?
Yeah.
Okay, thank you.
Yeah, yes. Actually, another you mentioned that for Alibaba's case, they are care about the latency. Yeah.
Any more questions?
Yeah, if no questions, you can still find me in this event. I'm still here, yeah. Thank you.
Thank you so much, Mr. Yang.